all of our previous discussions was describing topological spaces, some examples of topological spaces in various ways, from base to topological spaces or from new topological spaces from old one. Now we will go to continuous mapping. We have already discussed about continuous transformation. We have told that if a geometric object can be translated continuously to another geometric object, then they are topologically equivalent. For example, a disk can be continuously transformed to a ball. So, ball and disk, these two are equivalent topological objects. For another example, let us consider the unit circle centered at origin in R2. Now, we can continuously translate it to a point centered at say 40. Now, let us consider, let us puncture R2, that is, let us take the away from R2 the origin. Then, whether we can continuously translate the circle to the circle which is centered at 40. No, we can't do this. So, here continuous transformation breaks, but we have to formally define continuous, what is called continuous transformation. We have already known from real analysis the epsilon delta definition of continuous functions, as well as we also know from real analysis that continuous functions are those which pull backs open sets to open sets. We will take this as the formal definition of continuous transformation. Let us come to slide presentation. As we described earlier, we now give the formal definition of continuous functions between two topological spaces. A function f from x to y between two topological spaces x and y is continuous if for any open set O in y, its inverse image f inverse O is also open in x. That is, those functions are continuous for which pullbacks open sets in open sets. The definition of continuous function can be described in terms of closed sets as well. Proposition: a function f from x to y is continuous if and only if f inverse c is closed for each closed set c in y. Its proof follows as inverse function behaves well. In fact, from this inequality its proof follows, that is, x minus f inverse k is equal to f inverse y minus k. Let us see this following example. Let x is equal to r with discrete topology tau 1 and y is equal to r with usual topology. If we define a function f from x to y by fx is equal to x, then what happens? In fact, this is the identity mapping from R to R. So, when from discrete topology to usual topology, then it is continuous. But if we come from usual topology to discrete topology, then that function is not continuous, because it can't take open sets can't pull back open sets to open set. For example, in discrete topology singleton sets are open, but singleton set in the usual topology is not open. Let us present some equivalent criterions for continuity. Theorem: let f from x to y be a function where x and y be given topological spaces, then the following conditions are equivalent. F from x to y is continuous for any subset A. F of closure of A with respect to x is contained in closure of f A with respect to y. condition C, for each x in capital X and each neighborhood u of f(x) in y, there exists a neighborhood v of x in capital X such that f of v is contained in u. The third criteria is generally called local criteria for continuity. If f is continuous at each point x belongs to x, then f is continuous whole over the x, and the second criteria is in fact a generalization of Hens continuity criteria, which we have already learned in elementary reanalysis or metric spaces. What is Hens continuity criteria? It says that a function R to R is continuous at a point x if for any given sequence xn converging to x, the sequence fxn converges to fx. Now let us come to the proof A if and only if B. If x is a limit point of A, then fx is a limit point of fa. It can be verified using sequence. Hence, f of closure of x A is contained in closure of fa with respect to y. Conversely, let K be a closed set in y and A is equal to f inverse K. Then f of closure of A with respect to x is contained in closure of fa with respect to y, which is equal to closure of f inverse k with respect to y. This implies that f of closure of A with respect to x is contained in closure of k with respect to y, which is equal to k, as k is a closed set in y. So, we have that A is contained in closure of A with respect to x is contained in f inverse k, which is equal to A. Hence, closure of A with respect to x is equal to f inverse k. That is, f inverse k is closed and therefore, f is continuous. Now, A if and only if C, the necessary part is obvious. That is, if f is continuous from x to y, then f is continuous at each point. Now, let us consider f is continuous at each point x belongs to capital X. Now, and V be a non-empty open set of y, and let us choose some x belongs to f inverse V. This implies that fx belongs to V. Then, by given hypothesis, there exists a neighborhood u of x such that fu subset of V. This implies that x belongs to u subset of f inverse V. Hence, x is an interior point and hence f is continuous. Using this continuity criteria, we can compare topologies. Let us see first the following question. Let tau 1 and tau 2 be two topologies on X. Prove that the identity map ID from x tau 1 to x tau 2 is continuous if and only if tau 2 is contained in tau 1. In fact, what identity map do? Identity map takes any set to that set. So, for that to become identity map continuous from tau 1 to tau 2, it must have the tau 2 will be contained in tau 1. Next, let us consider some questions. Let f from x to y be a continuous map. We have to find out whether or not it is continuous or not with respect to a finer topology on x and the same topology on y. So, if the topology of on X is finer, then continuity obviously will remain, and if the same topology on Y, then also it will hold. But for the quasar case, it will not hold. And last two condition is left to readers. Weak topology. Weak topology will be helpful for us in the future course, but let us define it here. Lemma: let X alpha tau alpha be a collection of sets where alpha belongs to I is an index set, and we have given collection of maps F alpha from X to F alpha such that alpha belongs to I. Then there is a smallest topology tau on X for which the maps F alpha are continuous. For the proof, a topology sigma on X which makes all F alpha is continuous if and only if it contains this collection script A is equal to F alpha inverse U such that U belongs to tau alpha and alpha belongs to I. Basis criterion: we can describe continuity using basis criterion also, using basis also. Given a function f from x to y and a basis script b for y, then f is continuous if and only if f inverse b is open in x for each b belongs to script b. One part is obvious. For the other part, let O be an open set in Y and script B be a basis for the topology of Y. Then we know that every open set can be expressed as union of basis elements. That means O can be expressed as union of B alpha, where each B alpha is a basis element. Hence, F inverse O is equal to F inverse union of B alpha is equal to union of F inverse B alpha, as inverse mapping behaves well under union. Since each B alpha is open in Y and open sets are closed under arbitrary union, we have that F inverse O is also open. Now, we present some properties of continuous functions. The following lemma shows that continuous map behaves well under composition. That means, if f from x to y and g from y to z are continuous, then their composition G compose f from x to z is also continuous. And the proof is very much easy. In fact, we have to show that G composition f inverse u, this is open. But look that G composition f inverse u is equal to f inverse composition G inverse of u. Now, since G is continuous, then J inverse u is continuous. Now, f in as G inverse u is an open set in Y, so f inverse of G inverse u is also open in X as f is continuous. So, this proves the theorem. We are continuing properties of continuous functions. Lemma: inclusion maps are always continuous. In fact, if U is an open set in X and A is a subspace of X, then inclusion map IA inverse U is equal to U intersection A, which is open in A by definition of the subspace topology. So, the proof of this lemma follows. Next lemma: if f from x to y is continuous and A is a subspace of X, then the restriction mapping f restricted on A is continuous as a function from a to y. Let us skip this proof. Again, we are continuing some properties of continuous functions. This is some important theorem. If X is a topological space, then Cx, the set of all real valued continuous functions, form a lattice ordered ring. Proof. So, we have to define an addition and a multiplication and a order relation on Cx. If Fg belongs to Cx, we define addition and multiplication pointwise, that is f plus g of x is equal to fx plus gx for all x belongs to x, and f dot gx is equal to fx dot gx for all x belongs to x. It can be easily proved that these new mappings f plus g and f dot g are continuous, and under these two operation, addition and multiplication, Cx becomes a ring. Now, we define the order relation on Cx. We define it as follows: f less or equal to g if and only if fx less or equal to gx for all x belongs to x. This relation makes Cx a lattice ordered ring. In the previous slide, we have discussed about the ring Cx, which is the ring of all continuous functions from x to r, and we have observed that this is a lattice ordered ring where the operation is defined pointwise. We can also observe that this is a commutative ring with 1. In fact, f dot g is equal to g dot x follows easily, and one identity element is the mapping 1 from x to r defined by 1x is equal to 1 for all x belongs to capital X. We know that in every commutative ring with 1, any prime ideal can be extended to a maximal ideal. This can be proved with the help of Jones lemma. But this is a famous result about the rings of continuous functions, that in any rings of continuous functions, that is in any Cx, any prime ideal can be extended to a unique maximal ideal. In fact, the ring Cx have so many interesting properties in mathematics so that it is an important subject for research also. In the following, let us discuss some important example of continuous functions. Let us consider this as a theorem. Let x be the closed interval 0, 1, then Cx becomes a complete norm linear space. Proof that Cx is a vector space follows from the above theorem. Now, if we define norm of f is equal to supremum of fx such that x belongs to f, then it can be easily proved that this is in fact a norm on Cx which is complete. In fact, as we have considered x as closed interval 0, 1, then the set fx such that x belongs to S is bounded. So, the supremum exists. So, we can define the norm. With this norm, Cx becomes a complete norm linear space. Now, this is an extremely important lemma. In literature, it is called pasting lemma. Theorem: let x is equal to A union B, where A and B are closed sets in X. Let f from A to y and g from B to y be continuous functions. If fx is equal to gx for all x belongs to A intersection B, then there exists a continuous function h from x to y such that hx is equal to fx for all x belongs to A and hx is equal to gx for all x belongs to B. Proof: let C be a closed subset of Y, then H inverse C is equal to F inverse C union G inverse C. Since F is continuous, F inverse C is closed in A and therefore closed in X, as we have considered A as a closed subspace of X. Similarly, G inverse C is also closed in B, as we have considered B as a closed subspace of X, and therefore G inverse C is closed in X. So, their union H inverse C is closed also. In contrast to continuous function, let us introduce the notion of open and closed mapping. What continuous function says? That continuous functions are those mapping which pull backs open sets to open sets. We say that a mapping is open if it sends open sets to open set, and a mapping is closed if it sends to closed sets to closed sets. Let us consider some examples. An example of a continuous function which is neither open nor closed. An example of an open map which is not continuous. An example of a closed map which is not continuous. Let us first solve this, the continuous mapping which is neither open nor closed. This is an extremely important example for geometric view also. This mapping will be also needed in algebraic topology. We define the mapping P from semi-open interval 0 1, that is 0 closed 1 open, to S1 defined by Px is equal to e to the power 2 pi I x. Obviously, this mapping is a continuous mapping because this is some trigonometric mapping, but this mapping is not open. In fact, if we consider the set from 0 to 1/4, 0 closed 1/4 open, this subset of 0 1, then this is open set in the subspace topology, but its image to S1 is an arc whose one side is closed. So, that is not open. So, this mapping is not an open mapping. We can easily verify that this mapping is not also a closed mapping. Next example is open but not continuous. If we consider the identity mapping from R to RL, this is an example of an open map which is not continuous. In fact, the reason behind that, the topology of R is contained in the topology of RL. Same example works for to show that the mapping, identity mapping from R to RL is an example of a closed map which is not continuous, because closed sets of R is also closed sets in RL. This an example shows that every graph is a closed set in R2. So, what is graph? Let f from R to R be a continuous function, then graph of f is defined as x fx such that x belongs to R. This is a subset of R2. The picture of the graph of a continuous function f is shown in the following picture, and it can be easily observed that following picture that the graph is closed set. In fact, this can be generalized for some generalized case also. Let x tau be a topological space and yd be a metric space. If f g from x to y are continuous function, then this set all x belongs to x such that fx is equal to gx is closed. To see this, Let E is equal to all x belongs to S such that f(x) is equal to gx. We show that complement of E is open. Let y belongs to x minus E. Then fy not equal to gy. We can find open sets U and V such that fy belongs to U, gy belongs to V, and U intersection V is equal to empty set. Now F inverse U is open as G inverse V is also. So y belongs to F inverse U intersection G inverse V belongs to tau, but F inverse U intersection G inverse V is contained in x minus E, thus x minus E is open. Note that in the above example, if y is taken as Hausdorff space, then the result also remains valid. Next, we show that continuous mapping can be determined by dense subset also. Let x tau be a topological space and yd be a metric space. If fg from x to y are continuous and fx is equal to gx for all x belongs to A, where A is dense in x, then fx is equal to gx for all x belongs to x. Since A is dense in x, then for any point x outside A, there exists a sequence in A which converges to x. Now, image of this sequence under f and g are same as f and g agree on f, therefore, the result holds. So, after introduction of continuous function, we have discussed continuity and continuous functions. With this, we end this module.